Hello viewers, thank you for watching my channel. I'm back with another new video. Today I'm going to show you the Buchwald Hartwig cross-coupling reaction. In this video, I'm gonna show you a little bit background of the reaction and then mechanism of the reaction, and also I will show how to set up the reaction in a Schlank tube, and finally I will show a beautiful X-ray crystal structure of a compound which I made with this beautiful reaction. So let's see my reactions, and please subscribe my channel, and if you do that then I will get more inspiration to make more nice videos on organic chemistry. Let's see what is the Buchwald Hartwig cross-coupling reactions. The Buchwald-Hartwig amination or cross-coupling is a chemical reaction used in organic chemistry for the synthesis of carbon-nitrogen bonds. Remember, in my previous video you might have seen Hague coupling and Suzuki coupling, those reactions for the carbon-carbon new bonds, but here this specific reaction is for carbon-nitrogen bonds via the palladium catalyzed coupling reactions of amines with aryl halides. This coupling can be both inter or intramolecular, like same molecule or like two different molecules. Here I am showing one example. Here the aryl halide, X is the halogen. So X can be chloro, bromo, iodo or pseudohalogen like triplet, and R1, R2, so that can be alkyl aryl hydrogen, and R2 also can be alkyl aryl hydrogen. In presence of palladium catalyst and ligand, and with a strong base and solvent and sometimes heat required, or sometimes you can also do mild reaction to form this new carbon nitrogen bond. So this is Buchwald Hartwig amination reaction. The first palladium catalyst formation of this aryl carbon nitrogen bond was reported by T. Mijita and co-workers in 1983. But there was a disadvantage of early discovered reaction because they use stoichiometric amounts of tributyltin amides as a coupling partner, which is heat and moisture sensitive. Then MIT professor Stephen Buchwald and University of California Berkeley professor John F. Hartwig, who is a renowned organometallic chemist, and Buchwald is an organic chemist. They discovered this cross-coupling reaction, and they replace the tributyltin amide with a strong base. So in 1995, Buchwald and Hartwig concurrently reported that the aminotin species can be replaced with the free amine if the base is strong, like sodium tertiary butoxide, potassium tertiary butoxide, or LHMDS, that produce the corresponding sodium amide in situ by deprotonating the palladium coordinated amine. You can see in the mechanism, I will explain that part. An aryl bromide or iodide, while the palladium 0 catalyst is usually complexed with chelating phosphine type ligands such as BINAP, DPPF, JANTPHOS, and DPBP, or bidentate ligands such as DBA, which is trans-trans dibenzylidine acetone. Let's see the mechanism, how it occur during the reactions. So as a pre-catalyst, here I am showing palladium acetate can be used, and in presence of ligand, that can be tri-tertiary butyl phosphine as a ligand, and that palladium 2 convert to palladium 0 in the reactions, and aryl halide, here I am showing aryl bromide, attach in this palladium with a oxidative addition. You see the palladium 0, and now here is the palladium 2. So It is called oxidative addition. The first step is exactly like a Suzuki coupling or like Hague coupling. If you don't see those videos, please watch my videos on my channel on Suzuki coupling or like Hague coupling. So this first part is exactly the same. Now in this second step, the amine do the coordination with this palladium aryl bromide adduct. So here the lone pair of the nitrogen is coordinating with the palladium and forming this complex. And now you have to use a strong base like sodium t-butoxide or potassium t-butoxide. So that sodium t-butoxide is looks like this, and this oxygen will abstract this hydrogen or proton from this amine, and that the electron from nitrogen hydrogen bond is giving to the palladium, and since palladium is taking this electron, so bromine will be kicked out, and that bromide will be taken by this sodium ion. So ultimately the result will be the like t-butanol, like taking this proton with sodium bromide, as you see the t-butanol and sodium bromide. And since this nitrogen is getting attached with this palladium, so this called amidation, and this base is mediating to make this. So this step, third step, is called base mediated palladium amide bond formation. So ultimately it forms this adduct with this amine. Now still you see this palladium is 2 state, oxidation state is 2, and it will go to the 0. So it need to accept electrons. So this process should be reductive elimination. So in that case, aryl, palladium aryl, this bond electron will given to this nitrogen, and the palladium nitrogen electron will given to this palladium. So ultimately the palladium ligand will be as a ligand palladium 0 condition, and by reductive elimination you will get the final product as a amine. This is the final product of the amine. So this is a very nice tool to make the new carbon nitrogen bond, and this is the mechanism you are seeing. Next, see that what kind of reaction you can do. Here I am showing one of my reaction I have done with this Buchwald Hartwig reaction. So here I have tribromo compound here, like hexaphenyl compound, but 3-bromo, and I am using diphenylamine in presence of palladium acetate and tri-tertiary butyl phosphine ligand as a salt, HBF4 salt, and sodium t-butoxide. Solvent is orthoxylene, and it was done under reflux condition to make this three new biphenyl connected amine. So conditions can be bromo compound can be taken as a limiting reagent and 1 equivalent, and diphenylamine can be, since 3 I need 3 of them, so 3.2 equivalent, little bit excess. Palladium acetate is 15 millimole percent, and ligand should be 60 millimole percent, like 4 times per palladium, and sodium butoxide is 3.5 equivalent, and orthoxylene is based on your reaction scale, can be 30 ml, can be 40 ml, can be 50 ml. So whatever the reaction amount I used for 30 ml. And since it is a it has some solubility issue because of many aromatic rings, and it needed to be like connected 3 different position. So that's why it was little bit yield, but normally for a Buchwald Hartwig reaction gives very good yield, but for this specific reaction it shows less yield, but still I got the product. I will show the product X-ray crystal structure. Now let's see how to set up the reaction in a Schlenk tube. So here I'm taking solid materials, like whatever the solid you have, like starting material, limiting reagent, catalyst, ligand, everything, whatever the solids are there, just take those solids in a Schlenk tube like this, and once one by one you can add all of the solids in the Schlenk tube. It is an example like how to use a Schlenk tube for setting the palladium catalyzed or any other heating reaction in closed shell. So here I'm showing I am adding all the solids in the Schlang tube. So you can add by making the weighing paper like this funnel in the Schlang tube, and make sure that you have the this weighing paper up to down, so that all the solids go directly inside the Schlang tube. And once it is done, so make sure that everything is added, and after that I'm gonna add the solvent in this Schlang tube. And before adding the solvent, I can do also the little bit quick degassing process by using the vacuum pump. So now I'm closing it, so I can connect a tube here, and with a vacuum pump I will degas it while those are like in solid condition before using the liquid. So once that vacuum is done, then I can add the solvent in this system. So here I'm adding the solvent. You might see I am adding solvent while the Schlang tube is open. So still I need to do the vacuum degassing part, so that whoever have the freeze thaw pump system, you can easily do the freeze thaw pump system. So freeze thaw pump basically is like you will close this tube like this cap, and then you need to connect the side arm with a vacuum pump in closed condition, and then freeze it and with a nitrogen, like liquid nitrogen in a container, and freeze the whole thing tube in this liquid nitrogen. And once it is like solidified, then open that screw cap from the top and connect it in a vacuum pump, and then degas it. Once it degassed, then close again the cap, and then you can close the vacuum line, and then warm it to the room temperature. Wait for like couple of minutes, 15 to 20 minutes, and it will be warmed up. And do this cycle 3 times. Like you will freeze it, and then open the vacuum line from the manifold, and also open the cap from the, like little bit loose the cap from the top of the Schlang tube. And once, like for keep 2 minutes once it is solidified in liquid nitrogen, and then keep close it again, close the cap and close the vacuum again. And here I'm not showing the freeze thaw pump, it is like normal degassing process. But if the reaction is very sensitive, if you have used the palladium catalyst, here you can see the link I am showing here. So that link is one of the palladium catalyzed reaction I uploaded in my channel before, so you can see that video. So by the freeze thaw pump, you can do like degassing part. Once it is done, then put your Schlang tube in a whale bath or like sand bath or heating source, and turn on the heat, and make sure you put a shield just in the front of the reaction system. So here I set up the reaction, and I started stirring, and also the temperature. So this is for overnight reaction or like minimum 12-hour reactions. And once it is done, then you can cool down the reaction tube, take out from the whale bath or sand bath, and then very carefully open the cap from the Schlang tube, and then you can start workup according to the procedure. Normally, if you do the palladium catalyzed reaction, you have the base, you can add, based on the functional group sensitivity, you can add either water or like sometimes like 2% hydrochloric acid aqueous solution. So again, based on other functional group present in the compound, you can quench with the water, then extract with the DCM or the ethyl acetate. So here the basic setup process for these reactions. And by the reaction like I have done, I got a nice compound, and you can see the crystal structure. So here you can see I made the compound like this is the nitrogen, the gray bluish color is the nitrogen, so this is the nitro group. So and this is new connected biphenyl nitro group with the bromo compound. So this is a very nice compound, propeller shaped hexaphenyl benzene ring, and the nitro nitro group is connected here. So these are nitrogen, and this is also nitrogen, and red atoms are oxygen. So a nitro group, and here the biphenyl amine group connected with the bromine of the phenyl group. So yes, here I'm showing the extracrystalline structure, crystallographic structure, and you can see different way, like if you click here, like in publication mode, in presentation mode, and also you can show the ORTEP ORTEP for the SI material if you want to show. So this is the ORTEP, and also you can see in 3D version and work versions. So crystal structure can be shown in different software. So I will talk about later about the extracrystal structure opening software. So till then, stay fine, and if you have any question, you can ask me in your comment box, in the comment box, and I'm happy to answer those questions. And please subscribe my channel to get more video on more organic chemistry tutorial. So I think that's it for today, and stay safe and fine, and bye now.